So welcome to the session this morning. I'm not from ESA, so we are missing still Wim Zillik's from ESA. So we just start, I think. But he's coming now. Okay. Wim, should I go on or?
Oh, you started already. That is good.
Sorry.
Thanks, Dr. Steinbach. Yeah, shall we give it a go? If everything is right, we have people joining online as well. Hopefully, many of them. Welcome to this material science session. We have a couple of them today, where we go through the material science projects at ESA. Altogether, there are about 18 different projects today. I think it'll be somewhere between 6 and 8 we'll present. So it's not complete, but it is representative. And well, before forgetting, my name is Wim Zillik. I'm with the European Space Agency and moderating this session for you today. We'll start with alphabetically, more or less, with the SETSOL project. This is how it was arranged, so keeping it easy. Presented by Dr. Reinhardt from Aix-Marseille.
Thank you very much, Wim, for this kind introduction. So, good morning, everyone. It will be my pleasure to start this session on material science by presenting our recent activities within the framework of the ESA project SETSOL. I am currently coordinating this project following the retirement of Gerhard Zimmermann from Access. So, this will be the outline of my talk. I will start by presenting some generalities about the columnar to EQAX transition. It will be things that you might already know, but it will just be helpful to put things into context. Then the SETSOL project and recent activities within this project, and then summarize and present our future works. So, the columnar to EQAX transition, well, it occurs when you have grains, dendritic grains, that developed in a preferred direction. And when these grains are stopped by grains that developed in an isotropic manner, so-called EQAX grains, well, you have a transition from a columnar to EQAX grain, a columnar to EQAX transition. So this feature is well known to occur in God castings, as you can see here in this picture, but it also can be found in other processes, such as welding, as you can see here in this picture, also in other processes, even more complex processes, such as additive manufacturing, as illustrated over here. So this transition is rather complex to understand and to study because it involves several dynamical phenomena and would add at different scales, from the nucleation of grains to the grain growth and interaction, orientation selections, grain competition, and also gravity-related effects such as buoyancy and fluid flow. So it's a rather complex things to study. And in order to simplify things, one way is to use a configuration called directional solidification that can be performed in so-called Bridgman-Stockbarger furnaces, which consist basically to put a sample into a furnace composed of two heating zones, a hot zone and a cold zone, so that it will be partially liquid and partially solid. And then the main advantage of this configuration is that it allows us to control the main parameters of the solidification, which are namely the temperature gradient, the composition, and the pull rate. And so solidification can be triggered either by pulling the sample in the cold zone, or you can also imagine that you can move the furnace, and also you can also solidify by decreasing the temperature of the heating element. So it's a good way to control the solidification, and you can see here a nice illustration of a CET that was used using this technique, where you have columnar grains for a low pull rate of 2 microns per second, you can see nice the columnar dendrites. And then after increasing the pull rate by a factor of 10, you can see that it triggered the nucleation of new grains and a columnar to EQX transition happened. Well, that's the main idea, but obviously things are not that easy in real life, mainly on Earth due to the occurrence of gravity-related effects that I previously mentioned. So here are a few illustrations of these gravity effects. First one will be the impact of convective flow. You can see here a picture recorded during the solidification, directional solidification of a gallium-indium alloy. And when you solidify, you reject gallium that is light, and this light solute in the liquid will tend to go up and create these nice so-called solute plumes that will interact with the solid. And then you can see that it disturbs a lot the development of the microstructure and can even create liquid channels inside the mushy zone, the half-solid, half-liquid, partly solid, partly liquid zone. So it has a major impact on the development of the microstructure. This was in a model gallium-indium alloy. It's nice to see that we observed the same in a commercial alloy, CMS64. You can see here in this video the solute plumes drifting from the right to the left, and you can see how it impacts the growth and the velocity of the dendrites. So it has a major impact on the development of the solidification microstructure. So you have plume segregated channels and growth velocity variations. Second impact of gravity that I would like to illustrate is buoyancy. Because when you solidify, you have a solid and a liquid phase, and they usually don't have the same density. And so the solid usually is denser than the liquid, and as you can see here, grains that are heavier will tend to fall down in the liquid. But it is solidification, and so things are not that easy, because when you solidify, you reject solute. Here it is an aluminum copper alloy. Copper is heavy, so you reject heavy solute in the liquid, so the liquid will become denser and denser with time as long as you solidify. And what could happen? Well, it will happen that after a while, the solid that was denser will become lighter, and the grains that were initially falling down will tend to float due to this density inversion and due to this enrichment in heavy solute of the liquid. So that's an effect of buoyancy. Another one will be the occurrence of fragmentation. You can see here a nice aluminum silicon alloy with the columnar dendrite. You can see the secondary arms growing further and further, and after a while, well, what should happen? When they are heavy enough, they will tend to bend and fall down and induce fragmentation, which is something that we do not want because it can be at the origin of defects in the final ingot. So in order to, since we have a significant impact of gravity-related effects, then we have a need for microgravity environment to carry out benchmark experiments. And this is when the Quetzal project arrives. It's so-called, so it's the acronym of columnar to EQX transition in solidification processing. It started in 1999, so it's a rather old project, which was part of the microgravity application program until it stopped in 2020. It regroups a large number of academic and industrial partners, so that's one of the originality of this project. And the objectives are to improve the understanding of the columnar to EQX transition by carrying out solidification experiments in microgravity, mainly on two materials that are aluminum alloys and transparent alloys. So here I will focus on recent analyses or recent experiments that have been performed doing two batch on aluminum alloys, aluminum silicon and aluminum copper. This one is a bit older, but I will present recent analyses. This one was performed more recently, as well as transparent alloys. So regarding the aluminum alloy study, it was performed in the MSL, so the Material Science Laboratory facility. So you can see here a few pictures, but I think that Sonia will present this device also with further details in her talk. But here you can see mainly the cartridge, which where cylindrical samples can be inserted. It is 8 mm in diameter and rather long, almost 30 centimeters. And what's interesting is that it has 12 thermocouples, which allows a very accurate characterization of the temperature field. I will start with a rather old experiment, batch 2A. This batch we retrieved the sample, I think, in 2017, the last samples. And it was on aluminum silicon alloy. We have been studying CET, so there are a number of publications on these experiments. But here I will focus on a recent analysis carried out in these two regions, which are in the columnar area. Here you can see pictures of the columnar part that was solidified in microgravity. And we studied these two regions in details using a not so common technique, which is serial sectioning. So we selected these regions, we sent the samples to Peter Vory's groups at the Northwestern University in Evanston, USA. And they did this serial sectioning investigation, which consists in taking a sample to a milling machine. You remove one layer, then you take a picture at a microscope, and you go back to the milling machine, you remove another layer, you take a picture, and by stacking all the images, well, you can retrieve a grayscale image, a stack of grayscale images, and after some image processing, the idea is to obtain a 3D reconstruction of the volume. So this is what we got from this technique. So it's destructive, so we lose our sample, but we get nice images with a very good spatial resolution and size of the reconstruction. And what did we do from that? Well, here you can see more detail about this work in a recently published paper. But here, one of the main results was that it was possible to determine the structures that were connected with each other, deduce an envelope of these grains, and compare the position of the dendrites and the position of the fragments that were very tiny parts that were not connected to the dendrites. And it was possible also to determine the dendrites from which the fragments detached, and highlight the fact that the fragment density was higher where grains are the most misoriented, which illustrates actually the fact that grain competition, the impact of grain competition on the fragmentation phenomena. So once again, more details can be found in this paper if you have questions, of course. Then I will go to batch 3A experiment parameters. So these are more recent experiments. So the samples were retrieved in 2021. And you can see here a table of all these experiments carried out on aluminum copper alloys. So to summarize, 3 grain refined alloys were studied. We triggered the CET by applying a slow velocity, then either a velocity increase or a decrease of the heater temperature. And all the experiments finished with a fast velocity. Here you can see in this beautiful plot the temperature. So it's a bit difficult to read, so just keep in mind that the processing was nominal for these experiments, for all the experiments. And colleagues from the University of Miskolc have been studying these temperatures in details to retrieve the local temperature gradient at the solid-liquid interface, and also the velocity, the gross velocity based on these measurements. And what was obtained was that the temperature gradient varied a little bit, so it was okay. And what is interesting is that there is a transient stage before the growth front, before the isotherms reach the set point of the velocity set point. And this is something that we will see back in the grain structure characterization. So it was this transient stage will have an effect on the grain structure. And this is what we see here for 2 alloys, aluminum 4 weight% copper, and here aluminum 10 weight% copper. So for the 4 weight% copper, you can clearly see the columnar stage where we have nice columnar grains, and after the increase of the growth velocity, we obtain, as expected, a columnar to equiax transition with very small grains. And maybe you can see that grains over here are slightly bigger than grains over here, and this is due to this transient stage, this growth, this isotherm velocity that has been increasing progressively, and so the grain size also decreased progressively. When it comes to the 10 weight% copper and 20 weight% copper, this time we did not have columnar grains, but instead we had big, large grains at slow velocity, and then small grains at the higher velocity. So it was a transition from big to small grains. But this is it was characterized quantitatively in terms of grain size by the group of Access. And what was done also at Access was to measure an important parameter, which is the eutectic fraction, because maybe you can see it on the picture that there are areas that are white, areas that are dark gray. So white corresponds to the aluminum and dark gray corresponds to the eutectic phase. And by taking some small boxes and characterizing the fraction of this black and white region, we can deduce the eutectic fraction. And if we plot this eutectic fraction along the sample, and we collect the radial eutectic fraction, we can see that it is almost constant along the sample, except here, but here it is the initial seed that was, since the sample was partially melted. And what was interesting for us is that the eutectic fraction is almost constant all along the sample, meaning that there were no macro segregation along the sample axis, and that diffusive conditions were reached. And this is what we expect to obtain when we carry out experiments in microgravity. So all these experiments are summarized in a paper published by Gerhardt very recently. And obviously, since these experiments, we show that the experiments have been carried out in diffusive conditions, then they are a good candidate for comparisons with numerical simulations. And then I move to the third part on the transparent alloys. So there is an important activity in this project on the study of transparent alloys. There was a batch Quetzal 1 in the transparent alloy facility on the ISS, installed in the kinetic space glove box on board ISS. So the idea is to study columnar growth, then equiax growth, and the CET inside a transparent alloy, neopentyl camphor, for different, again, growth velocity, temperature gradient, and composition, since, again, with a directional solidification configuration, we can control each of them independently. And the gravity level was very good for these experiments. So here are some examples of some pictures of the cartridge. So you can see here the cartridge where the alloy is installed. Here it will be here the schematic again of the directional solidification furnace, with in the same way a cold zone and a hot zone, and the sample in between, and the field of view will be over here in between the hot and the cold zones. And what is nice when we use transparent alloys is that we can see directly the solidification when it occurs. So you can see here a picture of a columnar growth with tiny dendrites, and when we here in a close-up, we can clearly distinguish the features of the dendritic macrostructure. So here there were 100 dendrites. Sometimes, with varying the composition, we observed dendrites with a less usual morphology, where dendrite arms have been growing along 111 crystallographic direction. It happens. And if we look here at this video, it is an illustration of the impact of increasing the pooling velocity. So first we have a columnar structure, and then by increasing the pooling velocity, we trigger the nucleation of the grains that will stop the columnar structure. And then we increase 2 to 3 times the growth velocity, and you can see that the shape of the grain envelopes has been evolving, becoming more and more close to an octahedron shape. So again, you can see here the equiax grains growing successively, and then we increase again the growth velocity, and the shape, the envelope of the grain is changing to close to octahedrons. So what is nice with this experiment also is that the temperature profiles have been simulated, which is quite important if we want to carry out further quantitative characterizations, such as determining kinetic laws. If we try to relate the growth velocity of the dendrites with the undercooling. So it was done both for the eutectic and the dendrites. And this is interesting especially for 1-1-1 dendrites, for which the kinetic laws are not well known, and it can be used to compare with further theoretical models in the future. So this is what I wanted to show you about the sexual activities. So to summarize, we carried out advanced characterization in 3D of aluminum silicon samples. We also studied aluminum copper during batch 3A and reached a diffusive regime, so data is now available for comparisons with models. In situ observation of solidification in transparent alloys was also successful. And the CET analysis in this experiment is still in progress. And what are our future works? Well, it will be mainly focused on two last experiments. There were 3 remaining samples from the batch 3A on ISS, and the experiment has been achieved in 2024. So we are now waiting for the sample retrieval and analysis, except for the cartridge number 9, which had some a control issue, but we learned recently that it will be reprocessed next year. So we are looking forward to this experiment and to characterize the samples as we did for the previous one. Here you can see nice pictures of 3D reconstruction of a whole sample by X-ray tomography. I forgot the X-ray, but it's X-ray tomography to obtain 3D information on the grain structure. And also a second batch of transparent alloys has been carried out in June, if I remember well. So once again, it was very successful and focused on equiaxed solidification. So we are looking forward to retrieving the data and start the analysis, where we can see here nice pictures of the equiaxed dendrites with, again, a change from 100 to 111 orientation. Of course, this will have to be compared with ground experiments and numerical simulations if we have the manpower, because this will be an issue in the future to find the manpower to analyze these data. And also recently we learned that we have a sounding rocket campaign that should happen in 2027. It's a common Exermon-Quetzal project campaign. So Quetzal's with the study of combinatorial X-ray transition, and Exermon the use of X-rays to study solidification. But I will say a few more words about the Exermon project since I will be back for the last talk. So that's it for me. Thank you very much for your attention, and of course, if you have a question or request, do not hesitate.
Thank you very much, Guillaume. For sure, there are questions from the audience. Anyone? Let me then just make a small start. Sure. For CETSOL, you're using 2 instruments, 2 facilities we have on the ISS, MSL and transparent alloys. Could you explain how exactly they provide supplementary or complementary science?
Yeah. So, well, first you have the size, because with the MSL we can study bulk samples, so there are long diameter where you can reach permanent regimes, so you can solidify on a very long distance. Transparent alloy is a bit shorter and the thickness is smaller as well, but you have in situ observation. So the 2 of them are complementary, because on one side you have in situ observation in thin or not too thick sample that can be complementary to interpret what we obtain in metallic alloys on larger samples. Yeah.
Thanks. another one from my perspective then. You've been looking in the analysis
Yep.
to microstructure analysis. Is there any idea to link that to mechanical properties as well?
That's a good idea. There are a few groups that are doing that. There have been a few trials to do that, but I think this would have to be. We have to think about that before doing the experiments.
Yeah.
So one way would be to have. We could cut inside the sample and carry out mechanical tests, such as tractions and things like that. We will, but yeah, what do we do with the sample? Do we cut them and look at the microstructure? And to another issue is to have big enough samples to carry out tractions tests that are representatives.
Right. Yeah.
So yeah, we have to think about that.
All right.
Yeah.
So for now, you just rely on the existing models like whole patch, smaller grains give
Yeah,
higher
but
strength.
it is well known. It is well known that the grain structure has a significant impact on the mechanical properties, for sure.
Yeah. All right. Last chance for a question from the audience. You may have noticed the session is 2 hours long. We have 4 presentations. So the schedule is actually less tight than what is announced in the program. Well, let's thank the presenter once more. And then we move on to the second MSL project, I say. Presentation to be given by Dr. Steinbach from DLR, Chills Physics in Space Institute.
Yes, thank you for the introduction and welcome to my talk this morning. Yeah, it's a great pleasure for me to be here and to give you a short overview on behalf of the MICAS team, a short overview of our solidification experiments in the material science lab on board the ISS. And so within the MICAS project, we would like to obtain a quantitative understanding of the effect of fluid flow on the microstructure evolution in technical aluminum alloys. Why fluid flow? Because when you're thinking about the technical point of view of solidification, this means casting, you have always fluid flow in the casting process itself because you cast a liquid alloy in a mold, or what was already introduced by Guillaume, you have buoyancy always present in a liquid alloy because you have alloy components with different densities and so on. And on the other side, why we are working with aluminum alloys. So aluminum alloys, of course, due to their unique properties, you will find it in packaging and transport sectors. And of course, it plays a key role in lightweight construction, and especially the transition to electrical vehicles. This creates a strong demand on aluminum in the automotive industry. So, and for example, I found on the web here some diagrams, and it's predicted that until 2050, the demand on aluminum will increase up to 50% plus, reaching 18 million tons. So, and this strong demand on aluminum can only be met by almost equal shares of primary and recycled aluminum production. And for Europe, this means that increase the production of recycled aluminum, of course, will decrease on the other side the dependency of the import of primary aluminum from third countries with a higher carbon footprint, and will decrease also the CO2 emissions, because for the production of secondary aluminum made from scrap, you need only 5% of the energy you need for the, compared to the energy you need for the primary aluminum production. So, but when you talk to the foundries dealing with casting primary aluminum, a mixture of primary aluminum, secondary aluminum, or just recycled aluminum, there's always a big but, as always. And because it is well known that aluminum alloys used as a recycled alloy, there's always iron enriched in these types of alloys, and they can economically not fully remove the iron. And when you cast parts from recycled alloys, it's observed that sometimes only 50% of the possible strength of the cast part is reached. And the reason was why, and in foundries, the element iron is under suspect to be the origin of a lot of casting defects like shrinkage, porosities, and so on, because during solidification of such types of alloys, so-called iron-containing intermetallic phases like this beta phase, it looks like needles in 2D, are solidified. Yeah? And the question is, okay, you cannot avoid it, iron, so you have to develop strategies to deal with and to live with the negative effects of this iron components. And here comes space in. So I'm not talking about foundry on the International Space Station, of course, but what we need is an experimental setup suitable for directional solidification experiments under microgravity conditions to understand, on the other side, gravity-induced effects like fluid flow is. And as a platform, we have chosen, therefore, the MSL facility. It's located on the International Space Station since 2009, and it's in principle a joint venture, let me say, between ESA and NASA. So MSL, it's, whoops, sorry. No. Where is it? Here. MSL itself, it's an ESA facility, and it's installed in the Material Science Research Rack #1 from NASA. Yeah? So this is what I mean with a joint project between ESA and NASA, and both are located not in the Columbus module, it's located in the Destiny module. Yeah, as I said before, working very well since 2009, so this year's the 15th anniversary. And MSR itself is operationally controlled by the MSR team in Huntsville, Alabama, whereas the MSL Ops team is located at MUSC, Microgravity User Support Center, at DLR Cologne site. Okay, just a short overview of the facility. The rack in the core part is a vacuum chamber, and installed in this chamber, here mounted on a base plate, there is a rod-like sample in a sample cartridge, and it's fixed to the base plate, and the only moving part, and this is a typical set of what we mean with Bridgman-type furnace facility, is the furnace facility itself. So there are existing different types of furnace facilities, LGF and SQF. I will not going into detail, but what you should know is the typical experimental process. So at the beginning of the experiment, under vacuum conditions, the heater zones of the different, in the different facilities will be heated up to the desired temperatures, and after some homogenization time, the furnace will be moved in this picture here from the left to the right, so that the sample will be molten. And then after, again, some adjustment, temperature adjustment, for example, and homogenization time again, by moving the furnace from the right to the left, the sample will be solidified. And this means what we mean with directional solidification. As I said at the beginning of my talk, we are interested in studying the influence of fluid flow. We use an additional feature of MSL. This means that within these furnace facilities, there's implemented a coil system, which induces a rotating magnetic field, so that in principle it acts like an electromagnetic stirrer. So we induce, during the solidification process, controlled fluid flow conditions. And this enables us to solidify the samples, one and the same sample, first part of the samples under diffusive mass transport conditions in microgravity, and the second half, more or less, of the sample under controlled convective conditions, so that we can compare the microstructures in one and the same sample, fluid flow or no fluid flow. Yeah, and this is just a picture I would like to share with you. This is Matthias Maurer during his Cosmic Kiss missions exchanging one of the MICAS cartridges. You will find this video also on the ESA website. And let me say, he has done a great job. Normally we will foresee 45 minutes for this crew activity, and he has done it in less than 20 minutes. Well done. So if you think about a candidate for reflight, put his hands on XRF in the future. Also, I think he will be a good candidate. Okay. So coming now to the experimental results. So over the years, we had the chance to perform 25 experiments in MSL within batch 1, batch 2A, and batch 3A. So especially in batch 3A, we have processed very successfully 10 cartridges, and we are waiting for the download of the remaining 4 of them. Hopefully we will receive a nice Christmas present, or in springtime we will see. What was the goals of these experiments? So on one side, of course, our main topic is to understand what is the interaction between a growing dendritic structure, a tree-like structure, this means a forest of dendrites, and what happens when we have a controlled fluid flow ahead of the dendrite tips. What is the interaction? How do they interact with the overall fluid flow? And here you see now the cross-sections of one sample. As I said before, top part was solidified under pure diffusive conditions, mass transport conditions, whereas here the lower part was solidified when the rotating magnetic field was switched on. So what you see is here, I hope you can see it, is in principle you look on the top of these dendrites, you see the cross-sections of the dendrite arms lying on a more or less defined network in a matrix, let me say. When the samples, you look here at the microstructure now solidified with a rotating magnetic field, you see a change in the dendritic network, but in the sample center you see the strong macrosegregation. And this is an effect of the induced fluid flow structure. Yeah, because your sample is not endless, you stir it, you have a fluid flow parallel to the growing interface, but because your sample is not endless, you will create convection rolls in axial and radial directions, transporting solid enriched liquid towards the sample center, and you will finally see the strong segregation in the sample center, and our colleagues in Leoben are able now, can now model these fluid flow structures and also the reaction of the overall structure of the interface with these fluid flow conditions. So not only in 2D, but of course in 3D. And what you see here also is what I said before, the rotating magnetic field, the segregation creates a more or less liquid channel here in the sample during solidification, enriched in this case with silicon. Okay, this is, let me say, a macro segregation or macrostructure effect coming out to the microstructure. And I think all in the room knows how to characterize such a dendritic microstructure. One parameter is the primary dendrite spacing. You can measure the space between the different stems, plotted here versus the different solidification velocities, in principle the furnace movement velocity of MSL. Here for comparison, microgravity experiments, samples solidified under pure mass, diffusive mass transport conditions and with fluid flow. And you see that when we switch on the rotating magnetic field, the spacing is drastically decreased. This is one important result of these experiments. Here I have shown you the results of binary alloy, but we found it also on iron-containing alloys and all other different alloy types. And here I will show you some results from our Hungarian colleagues. They processed under the same conditions, some experiments in their lab facilities. And what we see is, first point, the same behavior with fluid flow. Here from this blue line to this blue line, we see again a drastically decrease in the primary spacing. But the other important point is, you see here from microgravity to 1G, also normal convective conditions, let me say, there exists in principle no facility on Earth free of fluid flow. So and this means, of course, for all modelers, etc., you have to take into account the effect of fluid flow on the dendritic microstructure, on the evolution of it. The other parameter, dendritic microstructure can be characterized on longitudinal sections, is the so-called secondary dendrite arm spacing. This means the side arm spacing of your Christmas tree. And it is well known that these side arms, because you have not a fixed melting point, your dendrite is always in a solid liquid transition. It stays a while in contact with the liquid. It evolves. And this is a so-called coursing process. You can think about it, it's like the smaller dendrite side arms will be eaten by the bigger ones, depending on the curvature of the dendrite tips. Yeah, and so therefore existing theory that the secondary dendrite arm spacing, depending on the solidification time, evolves or increases with solidification time. You have more time for causing, with an exponent or time scaling law of an exponent of 1/3. Okay, checking now what are our results. First here, the red dots coming from experiments under diffusive mass transfer conditions, and they are all lying on this theoretical predicted curve. Great, we said. So we confirmed the theories. Then we switched over to the experimental results on the samples solidified with fluid flow. You think about fluid flow, increased mass transport, causing should be faster. So we see not only an increase in the spacings itself, but we found also a new scaling law, new time dependence with an factor of around 1/2. Yeah, this is also important point. You change now the kinetics in principle, and this has also be implemented in the models. So now we are coming to the results of the iron containing alloys, independently if the samples were solidified with or without rotating magnetic field. The green and the blue squares here, they are all lying on the 1/3 curve. So, and this was somehow astonishing because we will see, as before, a change of the fluid flow, a change of the primary spacing for such types of alloys. The dendrites interacting with these dendrites, with the fluid flow, but deeper into the mush, the secondary dendrite arm spacings were not changed. And this was somehow astonishing for us. We say, okay, at the top we see something, but going down deeper into the network, we see no effect. So what was the reason for this? So therefore, just go back, here you see a typical microstructure of such a sample in 2D, mica 3. The light gray phase or white phase, here are the dendrites in the matrix and eutectic, and here you see again, it looks like needles in 2D, the beta intermetallic phase, iron-containing phase. But when you think about a needle, you see needles, but when you look at the top of the tip of the needle, you should expect some black dots here, but you don't see anything. So therefore, we put the sample sections in our computer tomography to analyze the sample structure in 3D. And what we found is that the intermetallic phases are not definitely needles, they are platelets. Very long platelets, but very thin. So thickness is around 2, 3, 4 microns, but thickness can be 600 microns, so in principle filling the room between two dendrites. Yeah, and this is now what you can get in mind, or what picture you should have in your, what picture you should have is that these intermetallic flow phases blocks the flow deeper into the dendritic network, and on the other side is, of course, they are consuming the solute rejected from maybe disappearing side arms. Yeah, it's a doubled effect, but the biggest effect is, of course, the presence of the intermetallic phases. So these are significantly the origin of the decreased fitting abilities in iron-containing alloys. And to characterize it, we use these reconstructed cubes with a special software tool. We get some information about the so-called permeability. This means the ability of the liquid to go through such a dendritic structure. And what we received is here plotted, the permeability varying with the iron content of different samples, from 0 to 8% iron. And what we see is that with increasing the iron content, and this means with increasing the volume fraction of the intermetallic phases, the permeability is decreasing by more than an order of magnitude. And all the models told me this is a really big effect. And this has to be taken into account in the models now. Okay, this is the point of recycling alloys, and just in principle like an outlook. We have processed also match-3A hyper-eutectic aluminum silicon alloys. So this means that the primary phase solidifying is not primary dendrite, aluminum dendrite. Now the first phase precipitates as a primary silicon phase. And the question was twofold. On one side, because aluminum and silicon has more or less the same density, the question was, if you solidify such a type of alloy, what happens with the primary silicon phases? Are they floating up, sinking down? We don't know yet. So this was a point where we said, okay, this can be investigated only in microgravity. And the second point is more technology-driven. Can we push, in principle, the primary silicon particles towards the direction we would like to have them? So can we control with electromagnetic methods the separation of the silicon phase, push them to the outer surface of a sample to produce a material with an increased surface hardness? And here you see a longitudinal section of mica 3.1, and you see, yes, with a rotating magnetic field, we are able to transport the primary silicon phase towards the outer part of the samples. So this is, in principle, a method to produce samples with higher surface hardness. But this is still under investigation, and of course, we are waiting for the remaining 4 samples. Okay, this was just like an outlook of one of the topics within Mica's team. I hope that you get the point that directional solidification experiments in microgravity enlarge the database necessary to make progress in the theoretical understanding of modeling, of course. A lot of topics like fluid flow, dendritic, microstructure evolution, aluminum recycling compared to casting defects, columnar to aqueous transition already explained by Guillaume Reinhardt, because we are always on the way to new technologies. You need tailored materials. And also, when you think about future exploration missions, experiments in microgravity support the alloy and the process design. Because when you think about, for example, printing with 3D methods, spare parts on the moon, on the Mars, in space, you have different gravity levels, and this means also different fluid flow levels. This is one point, which can be covered also within the Mica's project. And the other side, on Moon and on Mars, you will have to use the material or scrap what is present there. Yeah, and then you are coming into this region of casting, printing, whatever, recycled materials. So, and what we are doing now is, of course, analyzing the samples, waiting for the other 4 samples. And for your information, Wim, at the moment we are starting or have started a project in which artificial intelligence should analyze the microstructure of such types of samples, which means normally you can analyze automatically, or you can difference between a dendrite and a matrix. And now the next step is to implement phases with totally different morphologies, like these intermetallic phases. And foundry industry just started Spira with the implementation of new permeability factors in principle in their in-house software, so that we ensure that the knowledge is transferred to our industrial partners. Okay, and at the end of my talk, I have to thank you for your attention from the whole Mica's team, and of course to a lot of people, which enables us to perform these experiments on the ISS. Thank you.
Questions? Yeah, in the back.
Hello, thank you very much for the talk. My name is Caroline Smith. Thank you very much for the talk. It's working. Maybe. There we go. I'll say it again. My name is Caroline Smith. I'm from the Natural History Museum in London, but I also am a member of ESA-HRE. And so I'm a geologist, mineralogist by training, so I love seeing dendritic crystals, and I very much like crystallography and things like that. But I have a very general question for this group, if I may. So we heard yesterday about the setup of the biobank for biological samples that have been experimented on the ISS and returned to Earth, and those will be banked in an archive that scientists in the future will be able to access those samples for doing new types of experiments or different types of experiments from the ones that were originally carried out. Is there any plan to have materials that are created within the material sciences parts of the ISS science, so after you have completed your studies, to archive those materials So they are then available for other scientists in the future to use new techniques. So I have done a lot of computer tomography myself, and even in the time I've been doing it, we see advancements in the instrumentation, the software. You can look back at samples you looked at 10 years ago, and you can get new information. So my question is to you as the community: do you think having a material bank or archive of these types of material would be useful? And what would you see, if you do think it is useful, what would you see would be the best way to do that? Is that something that I can push ESA to say you need to start thinking about doing this? So sorry, it was a bit of a long comment and a question, sorry.
So in general, of course, we store the samples for many years, 10 years and above, in our institutes, of course, because as you said, sometimes after some years you think you have a new method, you will restart to analyze these samples with new methods. But of course what we are missing is, and this is definitely my question to ESA, one common place where we can store the materials itself and maybe the raw data, etc. So for example, MSL processing data are stored at MUSC, for example, or at NASA for 10 years. But the question is what after this time will happen to the data. So I would say from my point of view, yes, we need a storage place for the materials itself and also for the raw data.
Yeah, to link to that, this is indeed a very topical and relevant issue. It was mentioned yesterday in the presentation by Angelique van Ombergen that ESA is building up a long-term data storage system. This is being done at a university in Spain, and they're for now trying to capture previous experiments. What Sonja mentions is that for MSL experiments, the data that are gained from the actual experiment are temperatures and speeds. They are of no use whatsoever in themselves. It needs to come with the sample. And this is a particular issue. For other payloads, it's quite different. If you have observation, you capture all the images and you're all set. But for material science, it's a specific problem that the samples contain sometimes 100% of the scientific information. And that is with the scientist. And now the idea is more and more to make these data more publicly accessible. And so what to do? In principle, the samples are owned by the scientists. And so we can, as ESA, only rely on the cooperation of the scientists in what they would like to, let's say, keep for future generations. And of course, this is always on top of the daily activities, and so difficult, but it's a very important thing. And I always say, if a scientist retires at some point, he has two options: to put his data in a box or to preserve it with our data archive. And I think that the latter should be the better solution.
Sorry, just to go back to that though, my concern is, thank you. My concern is that, hopefully there are clear data management plans for the scientist who is retiring or leaves to go to another institute.
Yeah.
Okay, but geology and mineralogy is a material science. We need to be able to do science in the future, those physical samples that may have been created 10 or 15 or 20 years ago now. So who is responsible for ensuring that those physical samples, the bulk samples, microscope sections that have been prepared, any of the subsamples that have been taken, who is responsible for making sure those don't end up in a box and somebody in that institute in 10 years' time says, what is this box of stuff? It's going in the bin.
Exactly. I think this responsibility is not well taken care of right now. And I must say what Guillaume mentions, in some, maybe most cases, in the end, the sample is lost because you use destructive techniques to analyze. And so, then there's no way of resolving it. And it comes with a variety of very practical issues. I know that for our EML facility, it takes images with a high-speed camera. The archive wants to keep it in a generic format. But in the beginning, they opted for a different proprietary system because it captures the data better. And so then you have to transpose all that to a generic, let's say, way of format of the images, which can be problematic as well. All right. More questions? From my side then. I have a couple. You're not off. You're not off. You mentioned a foundry on the ISS. This matter sometimes comes up. We have these early concept teams, and they come up with ideas like we capture old satellite frames from space, and then we recycle them on the ISS in a foundry. But if I see what a little bit of iron does to your microstructure, I can ask you what is your thought about that, but I do think that I already know the answer. This is a difficult one. And then a real question, all this points in the direction of thixotropic processing, no?
Yes. Yeah. For example, we performed also experiments with aluminum silicon copper alloys, which are normally used for thixoforming processes, yes.
Yeah, but thixotropic is very heavily stirred, and you look for a mild way. Is that it?
Yep.
Okay. All right. If no more questions, we move on to the next presenter and also to a different ISS facility. Thank you again. So, and we move to a project by the name of METCOM. We have fantastic acronyms in our area. METCOM is the next in line, and this one will be presented by... All right, Johan, take it away.
Can you hear me? Yes, okay. So, dear Mr. Chairman, the audience, the people beyond the screen, I wish you a warm welcome to the presentation for METCOM. And I will give you a short overview about this project because it was a very long time. And then I give you a short overview what's happened in the last time. So I believe everyone is more or less similar to peritectic systems, but nonetheless, I will give a short review. In the peritectic system, here you have the peritectic point, peritectic temperature, peritectic concentration. At this point, liquid and a solid phase goes into a new phase. So under special conditions, especially if both phases, alpha or beta phase, are more or less in the metastable phases, and the sulfidification rate is very slow, there are some open questions. Additionally, what's happened with inclusions in the liquid? So here you can see metal quenched, and here you can see this different things, like here we have the initial alpha phase, here we have a band of the peritectic phase, and how this occur. This was one of the questions of this METCOM project, and since this is by a thermosolidal convection influenced, microgravity experiments are required. So I will give a short overview about all the project partners, what they did in the last year, and then we are going a little bit more in details my work at the university in Leoben. And since we have a little bit more time, I can go a little bit slower. Original, I calculated 20 seconds per slice. Okay, now for the first slice, of course, yeah, because this is very simple. Here you see the original structure of the project, more or less 2000. Is it divided more or less in two things? Here we have with metal and organic peritectics. This is the work of Professor Ludwig, and I make my PhD by Professor Ludwig. And then we have on the DLR and here, especially for in industry, working on inclusions. And we have a simulation part. Okay, during the time, the right side disappear, more or less, they finished their project. We get new partners, new members. The coordinator is changed now to our university. This is the reason why I present here this project. And yeah, this is at the moment the last structure. I hope this is correct. I'm not in the position to know all. And you see, this is the old members. These are now the new members. We get a little bit less and less. Okay, so now let's go to the DLA of Dr. Kolbe. The main topic of his investigation was what's happened with inclusion during periodictic solidification. So I go here very fast forward because this is not my topic, but it's a workshop here, and therefore I like to keep in mind for ESA what's happened the last year. I believe Wim even not so familiar with this because this is very, very long ago. Okay, he make his microgravity experiments, and here are some small snapshots about the inclusions in his metal alloy. Please, afterwards, don't ask me about this. I have no really idea. Then we have from our partners in Swiss, they make experiments with, you can see, copper and tin. Unfortunately, during his microgravity experiments, they have a bubble as soon as periodictic solidification started. Again, don't ask me details here. Then we have a new partner in Turkey. They want to investigate it from a binary to a ternary system. And this ternary system is one of metal and another one of organic material. And this organic material based on the results from our binary organic material. And the last one is a new partner from Nancy in French. And he starts in the last year again for using metals. And here we have the partner from Hungary. He makes phase field simulation according to periodictic solidifications. And here I will go a little bit more in details because his phase field based on our experiments, and he gave us inputs and we gave inputs to Hungary. This is a short overview under which conditions you found couple growth bands or anything else. So now coming to my work, and therefore I can go a little bit more in details. Here again, you have this quenched material, and you can see we use, instead of a metal, to observe the dynamic and organic material. This is TRIS and MPG. So same problem. Now, okay, going back. You can see we found this even under 1G conditions. We found here some bands. This here is alpha and beta, here the same one, and here we found it like eutectic growth, which occurs only if the solidification speed is very, very slow. We talk about micrometers in hours, yeah, that's have an idea, very slow. And the question for our work package is how this forms this periodictic coupled growth. We have here for metals, and the question is, how is the dynamic? And this here is now obtained under 1 microgravity conditions, 2021. So my colleague from French gave a short overview about the transparent LS device and the microgravity. So I keep it very short. It's a Bridgman furnace, like used for DLR, but we use an organic material. So we have 4 clamps, 2 hot, 2 cold, and we have approximately a 10 centimeter long cartridge. of cartridge of glass. And since we have very long experiments and we don't need the whole length, we divide this length in several sections, because to the missing of microgravity, there is no convection to the solidal, and therefore we have always more or less a fresh concentration which we can perform. So here we have now the detail of our organic material. This is the peritectic region. Here we have the elongation of the metastable phase. And these are the 4 cartridges that we use. Red 2021, don't like me. And the number 1 was performed 2023. Unfortunately, I make a mistake, put the wrong concentration inside. Yeah, okay, don't cut this from the video if possible, this part. Okay. So, since this was a compromise to Quetzal, because they need a long distance and a little bit thicker cartridges, we need a small distance between hot and cold to reduce the time of performance, and we use, as we like to have a very small glass sample to see through the organic material. Yeah, compromise is always a compromise. So in this case, we get here more or less different depths, because it's 1 millimeter depth, and we use at the university in Leoben only 100 micrometer depth. So here in Leoben, it's much easier to see it. In space with 1 millimeter, it's a little bit difficult. And since we have here 4 clamps, as 2 hot and 2 colds, they are not working absolutely perfect. There's a small deviation on temperature, which is normal. We get a small decline of the solid-liquid interface. And this leads, for example, to an MPG-rich channel. So this sounds bad, but on the other hand, we found out if we have a perfect sample, we see nothing of the dynamic, because then we are looking on a plane surface in the right angle. So now, okay, let me see how it works, as the technician said. No. Yeah, okay. Here you can see the typical solidification experiments in space. Here it's liquid, it's solid, and from this MPG enriched channel, the second phase coming like a wave, yeah, in front. And as soon as they reach the initial and alpha phase, they build here this structure, and this structure change during time. Yeah, without this decline of the liquid surface, we would only see a small black line and then this very nice alpha-beta phases. Unfortunately, it's transparent organic material. We cannot divide this, so we need how it forms. Yeah, here you can see original color, and then with improve a little bit the picture that we can see here the different phases. Here's a more or less a larger overview about that, and what we find out is that we have original initial alpha phase, which is an important thing to know it. That is really the alpha phase at the beginning, and not another phase. And then it forms the beta phase coming from this MPG enriched channel and try to overgrow the alpha phase. But then there's one question that we have between hypo and hyperperitectic. It seems to be that for the hypoperitectic phase, they grow more or less constant, whereby for the hyperperitectic phase, they form like here this triangles get smaller and smaller and disappear. But here still have open questions about this transient phenomena. Then, yeah, concentrate a little bit on the difficulties of this problem. And this problem, one of this problem is this peritectic phase. It's very flat, and you can see here This is the temperature inside the alloy, transparent alloy device. And the peritectic phase covers only this small region. So small mistakes on balance or local difference make a huge for us. Yeah, I see on your face you understand what the problem is. Right? You must be very precise, but we talk about always milligram and micrograms and all these things. Really not easy. And what we found out is another problem. We are not sure, is this a consequence of the material, or is this really depending on peritectic coupled growth, that we have a very, very long recoil. And even if we reach the first part where we have then dendrites, peritectic coupled growth, the solid liquid interface goes never in a stable situation. Steady state was never reached. Then if we compare this now with our colleagues from Hungary, they make a simulation, and the simulation here, these new concerns to the concentration within the hypoperitectic region. So they only investigated between C alpha and C beta, not in this region. And they say that the phase will change here from such a structure with is more or less a zigzag, where both phases are more or less equal, going down to less, and then more or less rods. Okay, so, and see, yeah, what we found out. We found the same one, but in one sample and over the time. We start here like this is more or less like a zigzag structure, as I showed you before from the phase field simulation, and over the time you can see here after 9 hours more from these batches we have more or less such small rods. Okay. So, okay, now this is more or less the important thing. We have many more details, but originally I have 50 minutes. And I calculated 20 seconds per slice. Here for this slice a little bit more. In short overview, yes, we have this recoil, which is not clear. It's depending on the material, or is this a consequence of the peritectic coupled growth? Professor Bass from Swiss, which makes the experiments with cafacin and has this bubble, also recognize a longer distance until the peritectic phase started to grow, but we have no idea is this a general effect or not. This is a completely open question. And we found that what was predicted by the phase field simulation. As we found the patches, we found that one phase overgrows the other one, and we found out that it's coming from this MPG enriched channel, so there was no nucleation observed on the solid liquid interface. Okay, and this was the last one that we have in this transition from patches to rods, but we found this in one sample over the time, 90 hours, means more or less 1 day work. And yeah, since these open questions, important for us is to get the opportunity maybe to use the ISS and the transparent alloy device as long as possible. And yeah, this is now the still open questions, as I mentioned before. And yeah, at the end, I said thank you to ESA, thank you to Red Wire to produce this. Thank you to all the partners. In this case, thank you to DLR too, and here, partners too. And yeah, with this, I finished. I hope you have no questions.
Thank you very much. Any questions?
Thank you. Oh, yeah.
Yeah, Guillaume.
Very nice space experiment. I was wondering if you try to do it on Earth, is it even possible to observe similar things, or do you have a ground reference test?
We found out such structures under. We found out such structures under 1G conditions too. You can see.
Yeah.
But if you compare this here are, let me say, peritectic couple growth. This is a mixture of peritectic couple growth and bands. And this is what we found out in space. So there's clear different. And without going more in scientific details, I believe this is the effect of the convection in front of the solid-liquid interface, that it gets smaller, larger, smaller, larger. Unfortunately, experiments in space are not cheap. So we have less experiments in space, and we cannot change the process conditions as fast as we can do it under laboratory condition on Earth. This is completely clear. Any other questions? Okay, thank you.
A comment from my side. In principle, there is the opportunity to steer the inclination of the solidification front, because the heaters can be independently controlled on both sides. But I can imagine that under space conditions it's very hard, because it's a trial error you can do and nothing more than that.
Yeah, the inclination, this is a good topic. As we start the first experiments, we have only polycrystalline structure. So you see nothing, more or less. You cannot see into the sample. This is only possible later on as the poly structure change into a 1 or 2 grain structure. Then we can see really that we have a inclination. On the other hand, we try to reduce the inclination, and the consequence was that we get only a small black line where we have a lot of problems now to interpretate the batches. We found exactly for these experiments where we want to reduce the incline, batches and words. So if we get the opportunity to make again space experiments, I believe one part will be to increase the incline. Yeah? I know this makes a problem concerning the concentration difference between the front and the back. But nonetheless, it makes much easier to understand how they formed.
Yeah. So it's an advantage in this. It was also suggested that it might be associated with the filling procedure, on if the cartridge was horizontal or vertical during the filling, which induced maybe some gravitational effects to, or concentration gradient.
Yeah, since I'm a metallurgy, I'm not really familiar with organic materials. Yeah? This is for me very tricky. For me, metals, very simple. Tin is tin, and if you make aluminium, tin, or anything else, this is, let me say, more or less clear. But for organic materials, there are impurities inside, there are chains, they are not atoms, they are molecules, so they make another different problems. But as yesterday, during the presentation, they asked how good is the ESA compared to other people. As far as I know, there's no organic, there's no model system available at the moment which give us the possibility to observe peritectic growth. There are different organic materials which show in their phase diagram a peritectic reaction. We tested it, but they are not really stable. Within, let me say, minutes, they get carbonized. So this is the only system, and we are the only one around the world, and the ESA is the only one has the possibility to investigate it by an organic transparent material to see the dynamic of peritectic growth.
Yeah, to follow up on that, it was mentioned yesterday already, but for the transparent alloys facility, we've done until now 6 campaigns, once a year typically, and that finishes the original idea of the program. Now, with ISS coming to an end, maybe 2030, ESA has now an initiative called Ready to Fly, and it means that we will prepare some more transparent alloys experiments. An announcement of opportunity for that will release within the next weeks. The thing for the scientists is there that they, even if they win the proposal, it's not guaranteed that in the end the experiment will fly. But I'm confident that if you have, let's say, your cartridge waiting for, there will be an opportunity to use it because, so we're hopeful on that. It will enable us to do 4 more cartridges on transparent alloys before 2030. Then one final comment relating to the previous question. Transparent alloys is a typical example of where all the science is captured in the images, and this goes directly to the archive.
Yes, well, there's a short remark. We make exhibition for the public in our city. So we go to a museum, and in the museum and thank you to the ESA again, they gave us 4 exponents, and we put these exponents, the videos on all what we found out in a very simple way to the public.
Mm-hmm.
Yeah. So, and yeah, according to the opportunity, life is hard, I know.
All right, good.
Thank you.
Thanks, Johan, once more. And we will be moving on to the last presentation in this session, which will be on ESA-HRE, one of the last letters in the alphabet. And Guillaume will be presenting again as the coordinator of this project.
Well, thank you, Wim, again. So hello again for those who were here at the beginning of this session. I'm Guillaume, and I will be presenting another project called ESA-HRE. So again, this will be the outline of my talk. I will start with a general context on the interest of X-ray imaging and present the ESA-HRE project. Then I would like to go through a few highlights of experiments and results that have been obtained in the past 3 to 4 years, and present works in progress on sounding rocket and the development of a new facility for the ISS. So we saw very nice pictures in transparent alloys. We can see that in situ observation with transparent alloys is very efficient. This has been, such alloys have been used since the 1970s and are still used as model of are quite a good model for the solidification of metal alloys. They solidify like metal alloys, but it is interesting to try to see directly into metals, and this has been made possible rather more recently, since the beginning of the 2000s, when scientists and started to use synchrotrons X-ray sources with a detector that has sufficient spatial and temporal resolution to visualize the features of the microstructure as was done with transparent alloys before. So this has been very successful using synchrotrons, and with the development and the improvements of the electronic devices and so on, what was done several years ago on using synchrotron is now possible using laboratory X-ray sources. And among the different techniques that have been used to carry out in situ observation of metal alloys, one technique is particularly successful. It's X-radiography, because it's rather easy to implement. All you need is an X-ray source, a detector, and a sample inside your experimental device. You put the sample in between the X-ray source and the camera, and then you collect with sufficient spatial and temporal resolutions a projected and magnified image of your sample on the detector. So this technique has proven to be very efficient to study several metallurgical processes, from liquid metal alloy diffusion to metal foam and metal alloy solidification. As you can see here, a few examples of radiographs that have been recorded by DLR, Helmholtz Zentrum in Berlin, and here our group. And so here comes the Examon project, which was then developed with the aim of not focusing on one single scientific topic, as most of the microgravity application projects at the time, MAP program at the time. Its originality is that it focuses on promoting the use of a technique, the use of X-ray imaging to monitor advanced metallurgical processes. So the main processes identified were metallic foam formation, diffusion in metallic melts, and solidification on metal alloys. And here you can see, since the beginning of the project, all the experiments in microgravity that have been performed. So it has been quite successful since its beginning and ending in the MAP program in 2018. And if you're interested by this, you can find an overview in a recently published paper in NPJ Microgravity. So we demonstrated the relevance of combining X-radiography and microgravity experiments, and I will show a few highlights of recent works that have been carried out on 3 selected topics. The first one will be related to diffusion processes. It's about the Soret coefficient measurement. So the Soret coefficient is a parameter that characterizes so-called thermodiffusion effects that you have when you apply a temperature gradient to an alloy, and through thermodiffusion you will have a migration of the different elements of the alloy. And this is the Soret effect is very well known in fluid dynamics. There are many works on transparent alloys and fluids, but it is much less common to study that on metallic alloys, especially in situ, as can be done with X-ray imaging. And this was done by our colleagues at DLR, who carried out the first Soret coefficient measurements on aluminum alloy, aluminum silver, where you can see here the capillary radiographs of the capillary samples. And again, by applying a temperature gradient to the liquid alloy, then you have a concentration gradient that occurs, which allows the measurement of this coefficient. So the values obtained was higher than by 2 orders of magnitude to the one that was expected. So there is still work to carry out in order to better understand this process. Process that has a particularity to demand long experiments, long time of experiments, and to this, its further works would require facility like the ESA-HRE facility that I will present in a few slides. But this would be a typical experiment to carry out on such a device. Another highlight that I would like to present is a work again by DLR and in collaboration with Access. It was carried out in the framework of the PhD of Thomas Werner. This work was part of the work of Elke Sonderman. So in this, it was a study on the interaction of hydrogen bubbles during the solidification of aluminum alloys as well. It is well known that in aluminum alloys you have hydrogen, dihydrogen that is inside the liquid and the solid. It mixes quite well with these elements, and so when you will solidify, you will have the formation of dihydrogen bubbles. And this study has been very rich in observations and results when looking at the interaction between the bubbles and the solidification front or within the mushy zone. Here are a few examples of results that have been obtained, such as the bubbles that induces a modification of the local temperature around. There is modification, of the local temperature field around the bubble, and it will impact the solidification front. Another effect would be a dendrite bending in the proximity of the bubble due to Marangoni flow occurring around the bubble. This Marangoni flow has other impact. It can induce so-called coronal outgrowth in the vicinity of the bubble, inducing, for instance, the formation of new grains or misoriented grains. And this perturbation can extend up to twice the diameter of the bubble. So the impact of the bubble is very significant. And also, what I find very interesting is a cryophile migration of bubble during directional solidification, because what we expect when you have such a dihydrogen bubble in temperature gradient, you expect the bubble to move up towards the hot zone. But what was observed is the contrary effects. The bubble has been migrated towards the cold zone, and this, after interpretation, illustrated the fact that both thermal effects and solutal effects have to be considered in order to describe Marangoni flow. And this, depending on the conditions, explained the fact that the bubble have been migrating toward the cold zone instead of the hot zone as usually observed. And last, but in two parts, recent results on EQUAXT solidification. Again, a work from colleagues from DLR studying the growth of aluminum copper and aluminum germanium alloys, but in an isothermal furnace. So there was a new device developed to fly aboard the standing rocket Maffeus, and it was the opportunity to study the EQUAXT growth of aluminum, copper, and aluminum alloys and compare experiments on ground and experiments in microgravity. And what was observed, there was a focus on the nucleation, the formation of the new grains and how they appear and their dynamics. And what was observed is that in microgravities there were distinct nucleation bursts, distinct nucleation events during the formation of the grain. But on Earth, the nucleation was more, the propagation of the nucleation front was more continuous. And this has been interpreted as an impact of convective flow on Earth. It is again an illustration that microgravity experiments, convective flow has a significant impact on the solidification and the need for microgravity experiments, because this convective flow impacts the so-called nearest nucleation distance, which would be the distance between a grain and the observation of new grains, because convective flow modifies the solute field around the dendrites and thus impact the nucleation process. And second part on EQUAXT growth, I would like to mention works this time carried out by our colleague at in Dublin, who also studied EQUAXT growth in an aluminum copper alloy using the so-called Exerman Sol solidification device, which was developed for the Maser 13 experiments, sounding rocket experiments. So the experiments are quite old, but the analysis is still in progress. And here you can see a picture recording during the microgravity experiments. And what is interesting currently is that the UCD groups in the during the PhD of Jonathan Mullen is actually applying machine learning to try to study the nucleation of each individual grains. And this gives this kind of very nice videos where you can see that the software identifies each grain separately, and it is then possible to follow the development of each grain. And this segmentation process is actually not so easy when using a conventional algorithm, and the use of machine learning in this case has been very successful, and our colleagues at UCD are keen on sharing this algorithm to apply it to other experiments. And finally, works in progress, so this will be the last part, but it will take some time also, about the preparation of a new sounding rocket experiment. So here in this slide, you can see all the ESA campaigns on solidifications. When you can see here, for instance, a picture of the very first in situ observation of solidification using X-radiography that was carried out in 2012. And since then, we performed parabolic flights, study of EQUAXT growth or CET in sounding rocket. And what did we learn from these experiments? Well, we should continue because it's very interesting, but also we should try to investigate other alloys. When I say other alloys, I mean different compositions, because so far most experiments have been carried out on aluminum 20 weight % copper, so it would be interesting to change the composition to 10 weight % copper or 4 weight % copper, which is closer to industrial alloys, or use different base materials. such as magnesium. This is what I'm going to present after that. And also a need for longer duration experiments, because typical solidification experiments can last several half an hour, 1 hour, and sounding rockets only provide a few minutes of microgravity. So there is also a clear need for long duration experiments for solidification and also for diffusion experiments, as I mentioned before. So regarding the use of another based material, there is a work from the colleagues again at UCD in Dublin, which investigated the relevance of magnesium zinc. Magnesium zinc is a good candidate, and it is part of a project called Magnesium Microgravity, for which has been selected for a sounding rocket after answering the previous announcement of opportunity for from ESA. So magnesium zinc is a binary alloy with a eutectic phase diagram. It's very similar to aluminum copper in terms of phase diagram and operating temperature. It is also, there is also a large density difference between the liquid and the solid. So in the same way, we expect thermosolutal and buoyancy effects on Earth. And it will be study on this alloy will be a precursor for space qualification if it is if we want to study this in other microgravity platforms such as a parabolic flight or ISS. So this will be the topic of a new sounding rocket, which will be Maser 17. So far what has been done, the idea is to reuse the previous Exerman Sol facility, which was previously used for aluminum copper. So it has been refurbished by the Swedish Space Corporation. It has been now shipped to Dublin. So you can see here a picture of the device. So it has been shipped to Dublin so it can be used on site. And it is now being restarted with initially experiments on aluminum copper samples just to check that everything is working correctly with the reference alloy. And then the synthesis of the magnesium zinc ingots will be is planned to prepare sample and then prepare this new sounding rocket that is expected to fly in 2026. So things are going well so far, and I expect it to be successful so far. But it will be interesting to study another base material that is magnesium. Especially, I did not mention it, but one of the main difference as well is that it has a six-fold symmetry. It's an hexagonal compact crystal compared to aluminum that is a cubic crystal. And so we expect a dendrite tip kinetic to be different. So it will be quite interesting to study the dendrite kinetic for a six-fold symmetry. And another project that I would like to present today is the development of the XRF facility. So XRF stands for X-ray Multi-User Diagnostic Facility for ISS. So you can see here a schematic of this device. It's a modular device. You can see here with an X-ray source and the experiment and an experiment unit where it will be possible to put different experimental devices. And the first experiment unit will be dedicated to solidification. So things are going quite well so far. Last year we had the breadboard test, where it was an opportunity to test different alloys that are well known and have been used before. End of 23, the PTR, the test review, occurred, and we had a rather positive outcome. So it was good to know. And last month, I was part of the endurance test. So it's been a 12-hour experiment. So the device was operated for around a bit more than 12 hours. We started at 5 o'clock in the morning until 9 in the evening, and things went quite well. But the data is still under analysis. Here, just to show you what it looks like, it will be the idea will be to study thin samples in order to have sufficient X-ray transmission. You can see here pictures of this new two-zone furnace device. So again, it will be directional solidification, with the idea that solidification will be triggered either by cooling down the heater temperature, which is what we usually do when carrying out X-radiography experiment, but what is interesting is that also it was implemented to allow pooling experiments. So it will be possible to move the sample inside the furnace in order to study the sample not only on the 5x5 field of view, but along a longer distance. So we will only see the top of the field of the solidification front, but we will see the evolution of the top of the front over a much longer distance. And these are typical images that have been collected here during the breadboard test. So the raw images requires some detector background and some additional processing in order to obtain very nice pictures where we can clearly distinguish the dendrites and the surrounding liquid. So in this new device, the image quality was very satisfactory, and the facility is clearly suitable to carry out in situ observation. So you can see here an example of a movie that was obtained. So it's a bit accelerated. The experiments lasted actually 15 minutes, but we can clearly see the directional solidification of and the formation of the grains in this aluminum 28% copper alloy again that was refined. And I do not know if it's clear at the very end. Maybe you can see this dark shadow coming from the bottom, which is the solidification of the eutectic front that we will use to characterize a bit the temperature field of the furnace in the field of view. And here is an example this time of a pooling experiment. So this time the sample is partially melted, so we have a liquid and the solid, and then it will be the sample will be moved toward the cold zone. So and you will observe, and we will observe the solidification of dendrites. So we only see the top of the solidification front, but clearly here it was low velocity, and we increased the velocity to observe the change in the microstructure. It was working quite well. You could see here the solidification front that is slightly curved. Maybe you can see that here it's lower than here, and this is typical of convective flow occurring during the solidification. So even if the samples are rather thin, there is still convective flow. And when we increase the solidification velocity, then the front is flat again, because there is we have to find a ratio between the characteristic velocity of the convective flow and the characteristic velocity of the solidification. And so hopefully it will be to reach quasi-permanent regimes during such an experiment. All right, so this is what I wanted to show again on this XRMON project. The application of in situ X-ray imaging to understand metallurgical processes is still progressing, which is good, at least for us. It is complementary to post-mortem characterization and in situ observation in transparent alloys, because when we are studying with X-ray radiography thin samples, which is complementary to post-mortem characterization on more bulky samples using metal alloys, or transparent alloys that still have higher spatial and temporal resolutions. I would like to mention that since the end of the MAP program, there is still a risk of losing contact between scientists and with the space agency. There is not much more motivation to carry out annual meetings, for instance. But in the case of XRMON, partners are still in contact, because we have been highly involved through our involvement in specific experiments, and especially so, as I mentioned, XRF in the future, MESA 17, and a common project with the Quetzal with a sounding rocket expected this time in 2027. So this is the end of my talk. I would just like to finish with a nice video, because this is what's nice with in situ imaging. We took a pooling experiment, and with using a trick, we changed the reference frame just to show that with a pooling experiment, we can have an image of the whole solidification of the sample. And since we plan to cycle the samples, remelt it and solidify it again, it would be useful to have an overview of the whole sample using such image processing trick. And that's it for me, and thank you for your attention once again.
Yes, thank you. Questions, maybe? So, yeah.
Thank you for this talk. So when you see such an image, how do you characterize the statistics of the average distance
between I see filaments, I see flakes, I see lots of things. Have you done some statistical physics analysis of each of the structure? You know,
Sure.
size distribution and
yeah, these are the same characterization as the one showed by Sonia in a previous talk. There are typical features, morphological features for these crystal grains. When we measure the primary spacing, which would be the distance between each grain, the secondary arm spacing, as you can see, maybe here there are secondary arms, so there are many models to characterize and compare these typical features that will have an impact on the mechanical properties, of course, of the metal alloy. So this has been done since many years on micrographs in the lab, on static images, and it can be transposed to in situ observations, of course.
So now for these activities, we have the luxury of a sounding rocket experiment coming up, 2027, and a facility for the ISS 2027. Would you still consider the sounding rocket experiment a precursor, or how do you position that versus the ISS work?
We still have to determine which alloy we will investigate in XRF. So the sounding rocket might still be relevant, and what it would be interesting in the sounding rocket, it will be the continuation of the previous experiment. So we studied EQX growth in columnar growth, EQX growth, CET, and it will be a new CET experiment. So this new sounding rocket experiment could be directly compared to the previous experiment, and if we retrieve the sample, it will be possible to, since it's a single shot, it's a one solidification experiment, it will be interesting to study the microstructure using conventional micrographs analysis from the sounding rocket. And on XRF, the sample will be melted and solidified several times, so we will lose the memory of the microstructure each time we remelt.
Yeah, indeed. And it will also enable us to test, let's say, the improved furnace.
And it will be a good opportunity for that as well.
Yeah. All right. Good. Maybe more questions. If not, that means that we will finish right in time in front of the queue for the coffee. And we will reconvene at 11:30 for a session on EML in this same room. All right, see you back later on.